Here's an interesting problem. We're going to look for patterns in these three different similar rational functions that we're taking the limit of as x approaches infinity. Ignore the scribbling up in the right corner. I couldn't get rid of that. Okay, so the first problem, part A, we're taking the limit as x approaches infinity of negative 3x plus 2 over 2x squared plus 1. Compare that to part B, the limit as x still approaches infinity of negative 3x squared plus 2 over 2x squared plus 1. And the last one, part C, the limit as x approaches infinity of negative 3x cubed plus 2 over 2x squared plus 1. The denominators are all the same, and the only difference is the power of x on the term negative 3x in the numerator. Now let's see how that causes us to get different types of solutions for each of these limits. For the first one, if we did a direct substitution of infinity, you can see what would happen. We'd get infinity over infinity. Indeterminate form makes no sense. We want to avoid that. Same thing for the second, same thing for the third. We never want to get infinity over infinity or infinity minus infinity. None of that stuff here. So we're going to do some algebraic tricks. Let's look at the first one. Our solution is we're going to divide the top and the bottom by the highest power of x in the function. It's x squared. So we'll distribute that multiplication of 1 over x squared on the top and on the bottom. Here's what we get. When we simplify it, we get the limit of negative 3 over x plus 2 over x squared. On the bottom, we get 2 plus 1 over x squared. You know that the limit of 1 over x to any rational power is going to give you 0. So we've got 0 plus 0 over 2 plus 0, which is 0. Next one, we're going to divide the top terms and the bottom terms by the highest power of x in the function, x squared. So we're dividing by the same thing. Let's see if we get the same answer. I don't think so. This time we get negative 3 plus 2 over x squared over 2 plus 1 over x squared. And that gives us negative 3 plus 0 over 2 plus 0, which is negative 3 halves. That's certainly not 0 like the first one. And the last one, part C, if we divided the top and the bottom by x squared, that wouldn't be good enough. That wouldn't help us. So we're going to divide or multiply the top and the bottom by 1 over x to the third. That's the highest power of x in the entire rational function. And let's see if that gives us something that's helpful. Anything to avoid infinity over infinity. Okay, let's do it. We get the limit of negative 3x cubed over x cubed plus 2 over x cubed, and then the denominator is 2x squared over x cubed plus 1 over x cubed. And we simplify that to the limit of negative 3 plus 2 over x cubed, and the denominator is 2 over x plus 1 over x cubed. Well, any constant over x to the rational power is going to give us 0. So we get negative 3 plus 0 over 0 plus 0, which gives us negative 3 over a slightly positive 0, which gives us negative infinity. All right, so let's analyze these three different results. For the first one, what kind of question did we have? Well, we had the negative 3x to the first power. We had the degree of the top smaller than the degree of the bottom, and that gave us a 0 result at the end. So there might be a pattern here to look at. For the next one, we had the degree of the top equals the degree of the bottom of the rational function, and that gave us a ratio of the lead coefficients in the top and the bottom. And the last one was a degree of the top is greater than the degree of the bottom, and that gave us an infinite solution, negative infinity in this particular case. I wouldn't say always just jump to that conclusion. Just show a little bit of work. You don't have to show every detail, but show that you know what's going on and where this came from.